All right. Hello, everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome, everybody. So we're back with a brand new topic. So I want to ask you, Mikey. I have this electron that's precious to me, and I want to break a piece of it and give it to somebody else as a gift. Like, can I do that? What's going on with that?
I think you could if you were like strong enough, but I have to qualify that by saying that strong enough. I don't mean like a human scale, on a scale of gods. I think it could be possible in principle. I mean, we've split atoms, we've split protons, and these are successively smaller and smaller particles. As far as we know, this particle called the electron, looks like it's not made up of anything. But everything looks like it's not made up of anything until you look at it closely, right?
Well, I think we should clarify that a little bit, right? So far, experimentally, nobody has been able to split the electron. Like, that's a fact. Like, so far. So I think we have to quantify this question. I guess we should think about this as...
We're not strong enough. That's
right.
What I'm saying.
But the question is, can we hypothetically split an electron, and what would that mean, really?
Yeah, so I guess to reframe that, like, why? I guess the interest of even splitting an electron, like, where did this fascination of like composite and fundamental particles come from? Was it just like as you keep probing smaller and smaller scales, or Tim, could you go through the history of that?
I'll have to discuss that. I should talk about the history, but I'm glad you asked, Sahil.
I think Mikey's slightly better with the history of particle physics than I am.
Oh yeah, because I had to teach a whole thing on like the history, so
I'll let Mikey take the charge. I think that's...
I have somewhat of a thing in my head, but like it's actually a practice that people have been doing since pretty much the dawn of time, right? Like ever since people realized, I can't imagine what their brain processes must have been like, but the first thing they notice is that there's a very regular pattern of the sun moving across the sky, right? Very regular, and it's very crucial for their survival. So they start praying to it, as anyone should. And once they realized that these simple cycles were, held inside them the information to predict things like, seasons and like when the crops would grow and things like that, things that were important for their survival. There's been this desire to like understand things in terms of their more fundamental components. So back in the day, I think, there were 5 fundamental elements, like earth, wind, fire, and planet.
Metal or something.
I mean, that's kind of the first attempt, right? I think it is actually the first recorded attempt to like explain everything from simpler constituents. It's just that more recently we've gotten really focused on this size thing, like what's smaller, right? We can break a rock up into pieces. We know we can break up those pieces into molecules. We know we can break up those molecules into atoms. We know we can break up those atoms into protons and electrons. We can break up those protons. So what's next?
Yeah, I guess the philosophy is that if you can break up something, that means that something that you had originally was made up of something smaller. And by breaking it up and studying its constituents, you're able to reconstruct the thing kind of in a more wholesome way. That's sort of the philosophy behind it.
And that philosophy has a name. It's called reductionism. And it's sort of been the guiding principle for at least particle physics, and I would say physics in general, since the time of Isaac Newton. Was the birth of physics, I would say.
Yeah, so let me just bring forth a contrasting point to Mikey. I think, on the other hand, I think given that we've tried so hard, and there's something a bit different, for electron comparing to like proton and say. So I would say that there's also good evidence to think that maybe electron really is just what it is. You can never really break it up.
Why?
Yeah, but of course, I mean...
I'm going to go hard on you. Why would you say that in a way that like wouldn't have been true when people were looking at protons.
Yeah, but I think there's something quantitatively different about protons.
What is
So we have to go back a little bit on the science that we understood back then when we had, let's say, the physics of protons. So we describe particle physics using quantum laws of quantum physics, and more generally we use these laws of quantum field theory. And the interesting thing about these quantum field theory, mathematics aside, is that these quantum field theories, they're actually not very good. They're very predictive. Like practically speaking, they're very good. In terms of making predictions, but theoretically, they're pretty bad. It's kind of like a calculator. Like a calculator is really good at calculating, but if you really dig in theoretically, calculators never do exact calculation. You can try sometimes. Let's say you look at 2 times pi, right? You only get some approximation of it. You get some digits, right? So that's the same thing with this so-called quantum field theory. The field theory is not complete. It doesn't give you the full answer. It gives you an approximation. And the thing is, sometimes this approximation gives nonsense. It gives you like infinities or some numbers that are just too large to make sense. And then,
oh wait, I should have said this earlier. Can we say quantum mechanics instead of quantum field theory?
yeah, okay, that's fair.
I feel like because what is quantum mechanics if not quantum field theory?
Yeah,
like no,
it is.
Yeah, let's not. Yeah, no one's gonna mistake. Oh, you're talking about non-relativistic.
yeah. Forget it. It just is quantum physics,
Okay.
right?
Yeah.
So okay. So the matter of fact is that the theory was sick. And the nice thing about quantum physics is that it kind of tells you how sick the theory is itself. So for protons, we know that the theory works pretty well back in the days, but we know that if we try to collide protons or try to split it, if you try to inject enough energy to a proton, the theory starts giving you answers that are kind of nonsensical, and you scratch your head, be like, oh, that's sort of weird. And then it turns out that the reason why the theory fails is because it turns out proton is not just one particle; it's not a fundamental particle. So that the theory is sick because of it. That's the reason, right? And so there was reason to expect that something was going to go wrong for the protons back then. You can apply the same logic and say, hey, is there something wrong with the electron? It turns out, there is something wrong, but way less wrong. Basically, we don't expect it. We don't expect the theory to go wrong until like basically forever. You probably never shoot enough energy to an electron.
Wait, is there anything wrong
there.
independent of the Higgs? The electron mass?
You mean the Higgs boson?
Yeah, I mean, if you ignore the Higgs, so if you don't know what it is, just ignore it. What's wrong with the electron mass?
Huh?
What's wrong with the electron? What's wrong with the electron in terms of like?
No. It just anything you calculate in a quantum in quantum field theory or quantum mechanics is approximate, right? So
I know, but you said that it doesn't have as bad problems as the proton, but it still has some. I was wondering what those.
Yeah, well, technically, the problem you look at is, for example,
I don't know any.
you can look at interactions, right? Like what's the interaction? And generally, a lot of times when you hit things at higher energy, the interaction gets stronger, and at some point it blows up, and that becomes nonsense. So for the protons, you can calculate back in the days, if you assume proton was one particle, fundamental particle, at some point the coupling blows up to super large. And for electron, all the couplings involving the electrons are pretty small, so it's not
a problem at all, I would say. Yeah.
Wait, what is the coupling?
It's just the amount of interaction.
The interaction, the strength of interaction, yeah. So like particles, every particle carries around a certain amount of energy with it, right? We can interpret that energy as its mass or as its velocity, its kinetic energy or its rest energy, for those are more savvy. If you look at the behavior of how much energy a particle has as you zoom into it, that's very telling about that particle. And what Tim is saying is that if you do that with a proton, very quickly you can see, oh, there's something wrong here. This thing must be made up of something smaller. But if you do that with the electron, you don't have any kind of such problem. I agree. Yeah, it doesn't have to be. But it would be like kind of weird, right?
Yeah, well, let me preface that a little bit. Maybe the audience is unfamiliar with this concept that, in quantum physics, sort of nothing is absolute. Like when you say electron has some interaction strength, it depends on the type of interaction you're probing it with. So that's why when we say, oh, the interaction can get stronger or weaker depending on how much energy you inject to it, that's precisely what we're talking about. Like there's no one definitive interaction. It changes depending on the process.
Is there some intuition to understand like why, like what at some like very small scale is happening? Is it kind of like positive feedback loop-esque, or like why is it when you pump more energy into a smaller space you get like, does that change?
It's kind of like the cutting a worm in half thing. You get like two worms, or like, if you try to, like, let's try to look at an electron very, very, very closely, right?
Yeah.
It looks like a point, but as I get closer to it, its electric field gets stronger, so the energy density there gets stronger. And when I get close enough to it, the energy density is so strong that it can at least pop out two electron and anti-electron pairs. So as I get closer to it, I start being surrounded by an everly increasing active bubble of electron-positron pairs because the density is so high. And so it's hard to tell what's the electron and what's not at that point.
Yeah, so
okay.
Yeah, particles are weirder than you think, actually.
I mean, they're kind of cute. They bubble.
Yeah, it's not like we have this conventional concept of a particle is just like a point, but it's not like that. It's like when you zoom in, it's almost like a mosaic pattern. I mean, we can never tell. These are just analogies, right? But the math kind of tells you.
It's very fractal, actually, right?
Yeah, the math kind of tells you there's sort of, it's not just like a dot, right? It's kind of like this mosaic-like stuff, cloud, or whatever going on. So that's why
we are legion. All of us are one of us, and one of us are all. That's what the electron says when you try to look at it closely. It starts popping out its friends, and then it says we are legion.
Yeah, but maybe Mikey, I'll flip the script on you. Like defend yourself. Why do you think we can split an electron?
I just think it would be weird if like you can split everything, and then sure, an electron looks like. And I guess this brings us to the point of like how tightly bound something is, right? Like a proton is kind of like a loose bag full of like these smaller particles called quarks, right? And it's not that tightly bound, so that's why you can see the problem so easily. So if the electron is composite, it's very, 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 very tightly bound, right? So tightly bound that it's so small that you can't see it's composite unless you look very, very closely at it. And at that point, what does that even mean? As we discussed, but what does that mean?
Yeah, so I guess there's sort of a little bit of a debate. Like, what do we mean when something is made up of something else? So I think in the case of proton, it's very clear because proton is kind of.
Wait. Let's get Sahil's thoughts on this, right? Before we jump into our. What do you think of when you flip the script? What do you think of when you think of something? Yeah. Well, what's your top non-particle example of something being made up of smaller things?
What about all like
Lego.
the mesons, right? Aren't they made up of quarks?
Oh, I mean non-particles.
Non-particles.
Or like, what does it mean to be made up of something smaller? It's actually like kind of a weird philosophical question. Like one of those things you think sounds simple. Like it sounds simple in elementary school, and then high school you think it sounds weird, and then college you realize it's actually simple, and then now that's actually weird again. What does it mean for something to be made up of something smaller?
I think that's a question that complexity theory tries to address, because they basically say you have all these different units that get together and you get some sort of epiphenomenon out of it. And so like we're made up of sort of non-conscious atoms. When you get enough of them in a particular order together, it like produces us, for instance, that can think and ask these questions. So I think it really comes down to the study of complexity, how things scale, and just how this it's greater than the sum of its parts.
That's a very highbrow explanation.
That's a very philosophical. Yeah. No, but
that's like absolutely analogous, exactly analogous to quantum mechanics. So I can't.
No, but look. I think we can bring it back to real life so that a relatable example. It's like Legos, right? When people think it's made of something else.
Right. Yeah, I think the reason why I say Hill's central because it's like I'm trying to convince you that there's something wrong with this idea of something being made of smaller things, but it's like, how can there be something wrong with that?
Yeah.
Like, is up not down? Is up not up? Is left not left?
Yeah, but let me just say we can actually try to define it properly, right? So there exists a definition that we can define such that the electron is definitively not made of something smaller, right?
Well, my definition, according to my definition, definitively made up of something smaller.
No, but let's connect that to intuition, right? Like normally when we say something's made of something else, it's like Legos. And what that really means is you have two Lego blocks, and it's not so hard to pull them apart, right? So normally what we say, this happens when the binding energy is very small comparing to the overall energy of the system. So these are, you can define that technically, right? So if you think of a proton, you can think of the quarks as kind of like, they're not so tightly bound together. So you can maybe pull one out. Like that's sort of the intuitive scenario when people say, hey, like the car is made of Lego blocks, right? Or like, my hand is made of cells because like they're not that stuck. But in this scenario, if the electron were really made of something else, because so far we haven't been able to split it apart, it would be analogous to, like, imagine you have two Lego blocks, and when you clench them together, the Lego blocks are so tight they actually just kind of melt into some weird mesh of, I don't even know what you call it. It's like when you put two Lego blocks together, the outcome is totally different from the two original Lego blocks. Like, that's the only possibility. Then I would argue that, can we even call that as, the final form being made of the original form? I'm not sure.
Wait, what do you mean? The final form depends on what the environment looks like, though. If the temperature's super high, then the final form could be exactly as you described.
Yeah, but I would say that we bring it back to real life. If, like, right now, right here.
Yeah, oh no! Of course. Okay, fine. Yeah.
So if you take that route, then the answer is clear. Like, we definitively cannot.
So then,
right
are you saying that the electron? It's possible that the electron was once a composite particle, but is no longer? Are you saying that's fair? Like because early in the universe, when it was super hot and dense,
then we don't know. I think that we don't know. That we can't tell.
Yeah, I'm not saying we know. I'm just but if the electron, if we take the definition that I'm talking about, the high temperature definition, right? Because like it's possible that what Tim's talking about is that, like, if you try to pull the electron apart at these low temperatures, it's so strongly bound that it's just going to give you like a mess of like extra stuff.
Yeah.
But they're not cleanly separable. But if you increase the temperature super high, it's entirely possible that you could separate them in the way that he's describing, and then it would be true that the electron could once have been considered a composite particle, but no longer. Okay, I mean,
what does it mean to increase the temperature? Like, do I get an oven and just like cosmic oven and just like turn up the dial and it just goes up?
Yep.
All right.
1 billion degrees.
Well,
literally.
Way more. Hold on. 1 billion degrees is not enough. We had created a billion degree. Trillion, in fact.
My superlative was 2.
Trillion is not even enough. We need harder. Sorry, yeah. Degree is not the right unit anymore, actually.
Yeah. So I want to ask some audience questions before we move on. How do you look closely at an electron?
Yeah. Well. Yeah. Well, the way to.
There's the way we do it, and then if you're thinking about in theory, like how could you examine it if you had like a magic school bus school bus type situation where you can like go into someone's.
Yeah. I mean, the most straightforward answer is it's simple.
How we do it.
Yeah. How we do it in particle physics, we basically focus a high super energetic beam and just blast toward it, and the smaller you probe, the higher the energy is. You just have to have a massive energy beam to blast it, and for someone familiar with photography, you might be familiar with the diffraction limit. Basically, the size of the light determines the details that you see. So it's the same thing here. In order to see more detail, the beam kind of needs to be more. The wavelength of the beam has to be shorter. It's to be more focused with more energy. So basically, you just have to blast it open. So that's why we keep talking
is there
about.
a simpler way to say it? It's like, okay, so in a sense, there's many forces that are causing these particles to not want to occupy the same space. Even if it's an electron and a positron, they're attracted to each other. But there's poly pressure. Sorry, that was completely wrong. Forget that.
Some interaction. No, it's not completely wrong, but okay.
Yeah, poly pressure. I think, but it's hard to get things really close. The only way to get things close, right? Like if you want to get things close that don't want to be close, you have to push them really hard, right? And at a certain point, if they're really repelling each other that much, the closer you get them is represented by how hard you smash them.
That's why particle physicists are obsessed with the energy scale. The greater the larger the number, the better. It's like camera megapixels. Yeah. I guess we're shallow like that. The more megapixels, the more energy.
Yeah, electrons and positrons are an interesting example because when we collide them, the reason why we want to collide them in higher energies is so we can get them essentially closer and closer together.
Makes sense. Makes sense.
But that's more about the time scale, right? It's like, because you have these, okay, so to answer that question less simply if we have time is if you collide them at as high energy as possible, you can imagine them going through the process of getting closer and closer to each other, right? And then in slow motion. And then it is that picture I described where they start to see each other's clouds, right? They get so close to each other that it stops making sense. But that can happen on such a short time scale that they still get close to each other before the mess starts, right? So that's kind of what we're talking about, actually, right? Does that make sense? Tim, is that a fair interpretation, actually?
I think that's fair. That's similar. Okay. It's basically similar,
The time scales are an equally good representation, right?
Yeah, because everything's moving at the speed of light at that energy. So space and time, same thing.
Basically not moving.
Yeah.
So I have another audience question. Is it possible for there to be any kind of totally fundamental thing that has nothing inside of it?
So we didn't quite get to why it's so sticky to ask about how things can be made of each other. Right.
Yeah. So that's a good question. The answer, unfortunately, is not obvious because it depends on, at the end of the day, we have to go back to what does it mean for something to be made of something else. Yeah. And unfortunately, the naive intuition doesn't make sense because, hey, for example, hey, if A can break into two pieces of something, is A made of that something else? But, that might seem true in real life, but in particle physics, it's different. It could just be an interaction that you created new particles or the particle decay into something else. Like for example, a cousin of electron, muon, can decay into electrons and neutrinos and all that. But we don't say the muon is made of electrons and neutrinos. It's not. It just wouldn't make sense.
There's a sense in which they are, though.
To some extent,
you'll see some electrons.
You can it's not clean. To some extent, you can think of them as muon could be a mix of electron plus neutrinos. But the reason we don't talk about that, again, practically is because the interaction is small. It's small enough that it doesn't make too much sense. So unfortunately, these questions are always not 0 or 100% in particle physics. It's somewhere...
Well, if you speculate a little bit, I think you can say, let me just speculate just a little. I would say it's likely that it's either the case that there's just one particle if you turn the temperature up to this highest possible level, and then that thing just decayed into everything else. And everything else is it's everything is inside of that fundamentally. Or there's nothing. It's just like this like a web thing where nothing is more fundamental than anything else. That will be my.
What do you mean by that? Like web of where nothing is more important than anything else or fundamental than anything else?
That's actually, I think, the more likely scenario. So, maybe it's worth describing that in more detail. This idea that, like, if you actually think about it, the idea that something is made up of something smaller is actually the same idea of sort of an extension of that particle. It's kind of weird. Tim, is this related to T-duality, the duality between large and small in string theory? I think it might be, actually, right?
I'm not sure.
I think that is a T-duality.
I'm not sure if I can think about it right now at this spot.
Yeah, but there's a sense in which something being made up of smaller things is equivalent to that thing actually being part of a larger structure.
Yeah.
Oh.
It's completely bizarre, and it comes from this, I think, string theory idea called T-duality.
No, actually, it's not that bizarre, right? Like, it's similar to the analogy we described, right? If A breaks into two pieces, there's a sense in which we can talk about A being made of two things, or A just interacts with two things. These are kind of, there's no right or wrong answer, actually. It just sometimes it makes sense to talk about one way versus the other.
I don't know if you can give that analogy of higher dimensional modes to Lego blocks. Okay, wait. So maybe we should just say that, like, in physics, it's bizarre. This idea of compositeness turns out to be mathematically identical to another description of the same particles that are, having larger structure.
So it is true. It's actually pretty understandable. The thought is that let's say the electron's made of something else, and it's so stuck together. Let's say electrons made of some constituents. They're super stuck together. We can't break them apart, right? So the only way to break it apart is to throw in a lot of energy to loosen them up, kind of, Then you have to inject so much energy into the electron so the electron gets excited. So let's say turn into excited electron. And then that excited electron can break apart and decay into two other things. So that's one way of viewing it. It turns out there's an equivalent way of viewing it. You can think of, perhaps you hit the electron, and instead of the electron getting excited, you can think of the electron move a little bit, jiggle a little bit in an extra dimension, right? And now it's got energy, it's got movement in the extra direction. And because it moves in the extra dimension, eventually those can decay back. Eventually it moves back, and that kinetic energy can get converted back to ordinary particles. It turns out,
hoping for a Lego block analogy.
Yeah, so it's like, is it composite? Like then you can play this game, right? Like let's say I discover something like this, at an accelerator. You found out that you can excite electron and it decays. Like, we actually wouldn't be able to tell them apart. Be like, hey, is it extra dimension? Is it composite? But
today I feel like the question is very similar to the question of, if I have a worm, how many worms do I really have? One or two. Isn't it? It's kind of like, it's like basically the string or the 2 points of the string. What do you want to consider to be the object here? It's like, there are these particles which we consider talking about called pions, which are these composite particles made up of two particles bound together.
Two quarks,
and should I think of those things as two particles or one string, with those 2 points being the end? There is kind of a line of energy between them, so you could argue that.
Yeah, it's like
the real string.
Yeah, it's like, is it the particle itself or the interaction between them? Which one's more important? But it's like you can't separate.
Entity?
You can't separate them, unfortunately. So
it's very new agey. It's like, it depends on how you want to define it.
I guess sort of our theme is that of duality. There's no one right or wrong answer. But in my opinion, if you look at real life, you can, your answer could be.
Don't say that, because it's not. People will take that. It's very exact and very precise, right? It's like
it's precise because it's designed to be, right. You can use the coupling as the determinant. It's a very practical.
Yeah, but it doesn't. It by no means means that nothing means anything. It's quite the opposite, actually. I feel like when people hear that kind of stuff.
Yeah. So guys, we're running very close to the end of this. So I wanted to ask you guys one final question. what is like the limits of this reductionism? Like, is there kind of a limit to just smashing particles together and figuring out fundamental physics?
Yeah, I think we're there. For the first time in 400 years. I don't know. We'll see.
I'm not sure. I think in practice, it's possible we can split more. I guess go deeper and deeper.
In
But
practice?
but like a limit right now could be completely technological and just
No,
matter
it's
of
completely monetary, right?
yeah, it's completely well. First of all, it's completely monetary. Depends on how much money we want to spend upgrading the accelerator. But philosophically, you can ask, what do you think the ultimate picture of physics, the nature is? I don't know.
In the 70s, particle physicists dreamed of a theory that where nothing was more fundamental than anything else, and everything was just sort of like defined by the transformations. Yeah. I think they were wrong at the time because they were trying to predict that protons weren't made up of anything smaller. But I think they're right in the end.
Yeah. I think my view is agnostic, right? I think I'm humbled by the fact that many theories we have, we were not able to prove them, and in fact, nature is like, nature is nature. Nature doesn't care. Nature knows. We're just trying to take pictures, and quite literally so. We're building the largest, most expensive camera in the world and trying to take pictures and see.
But nature is always more clever than you can imagine.
Yeah, exactly. So
if it was something silly like some particles are composite and some others, that would be so silly.
I feel like if nature has conscience, he or she would probably just be laughing at us, like, you think elementary particle composite extra dimension, how silly, right?
Yeah, we got slapped for that.
Basically.
We got slapped for thinking that. But with every slap comes insight, beautiful insight.
Yeah, we can dream.
Discoveries.
Yeah, I think at the end,
made from it.
At the end of the day, can we split an electron? Even though it doesn't sound like it, it's more like a human question, because we know that from physics the answer is ambiguous. We can't even define what we mean to split an electron. So it's like our question imposed on nature. So it's like, maybe, I guess, but.
Well, that's a very poetically positive way to end this. So with that, I'd like to thank everybody for joining us, and we'll see you all here next week, same time. Anything else to add before we head out?
Nope. That's it. Thanks for joining. See you guys next week.
Thank you.
Yep. Thank you, everybody. Bye.
Bye.